Greetings, my name is Aidan Stark and this is my ENME435 Assignment 4 project. For this project, I was tasked with creating an algorithm in Python utilizing OpenCV to detect lane lines on the road within two separate videos. In this video, I'll be showcasing the performance of my algorithm, discussing challenges faced, what I did to improve the performance of my algorithm, and what future steps I would take in terms of both software and hardware to improve lane line detection further. To begin, I'll show my algorithm's performance in the first video. Within the center is the main video of the road and the line tracking. Within this video, the magenta line represents the algorithm following the left lane line, and the teal line is the algorithm following the right lane line. Along the left and right sides, you can view the preliminary steps that the algorithm is taking to perform this lane line detection. First, I am masking off a section of the video so that the algorithm only focuses on that portion. This is done for three reasons. Firstly, it is how I distinguish between left and right lane lines. By having the algorithm process the left and right sides of the picture separately, there is no risk of it confusing the two lines. Secondly, it reduces the processing time by eliminating a large portion of the image that doesn't need to be processed. Thirdly, I have carefully set up the mask to block out the sky to ensure the bright sky is not confused for a lane line, which occurred in early development. After masking, I convert the image to HSV values as opposed to RGB values, and set a lower and upper threshold for what I consider to be white lane line pixels. In white, you can see what pixels pass the thresholds. I then blur this image to eliminate high-frequency noise. I perform edge detection on the blurred image. I define parameters for what constitutes a line. Lastly, I average all the possible lines into a single line. To more clearly show this process, I'll now show the entire production pipeline on a singular image. Here you can see the original test image, a snippet to try and eliminate the sky, which is not needed for processing, a masking to further eliminate portions of the image that do not need to be utilized. This is conversion to HSV values. These are the white pixels which pass the upper and lower thresholds to be considered white pixels. This is blurring it to remove the high frequency noise. This is the edge detection upon the blurred image, and then performing a hue transform. These are the lines in which were detected. What you see within the prior video is averaging all of these separate lines into one singular line to try and determine the true orientation of the lane lines. One of the issues I encountered when developing this algorithm was that the lane lines on the left would consistently disappear since it is a dashed line. To resolve this issue, I reduced the criteria for detecting a lane line to ensure that white dashes farther up ahead in the road would be detected. This involved reducing my original blurring from a 21 by 21 pixel square Gaussian blur to a 5 by 5 Gaussian blur. I used the function cv2.canny to perform an edge detection and lowered my upper threshold from 150 to 90 so my algorithm would be more generous in detecting something as an edge. My lower threshold was 30. Lastly, I used the cv2.huelines function to determine what constitutes as a line. In that function, there is a voting system to determine what will and will not be included as a line, and I reduced my number of votes needed from 30 to 20 votes, again with the intent of making my line detection more generous. Other than modifying my original parameters for lane line detection, I added memory to my algorithm and had it remember the last 25 frames of video, which is 1 second for this video. It would then use this memory and average the current frames detected lane line with the last 25 frames. This further helped the algorithm maintain the lane lines even if there were short periods where they were not seen. Additionally, since the lane lines were averaged over time, the lane line detection would transition smoothly even if there was a short gap in detection. I will now demonstrate the performance of my algorithm on the second video provided. In this video, you can see that the lighting conditions of the road are much different than the prior video. In initial testing, this proved to be a major problem because the first and second videos required significantly different upper and lower thresholds for detecting what pixels count as white lane lines. I took images from both videos and opened them up in Microsoft Paint to determine the typical HSV values of the lane lines and road within both videos. From doing this, I found that there was a significant overlap in the HSV values of the lane lines in the first video with the HSV values of the road in the second video. This meant that it was not possible to establish a single static threshold that would work for both videos. To get around this, I created a function in my program called getRoadColor that would look at a small section of the road directly in front of the car and average its HSV color. This color's value, and by value, I mean the value in hue, saturation, and value, would then be doubled and defined as a minimum threshold for white pixel detection. This ensured that the road would not be detected as white pixels and that lane line detection would automatically adjust for road lighting and surface conditions. I will now discuss some of the current limitations with my algorithm along with steps for future improvement. Firstly, by taking a snippet of the road for color detection, I'm assuming that there is nothing on the road that might interfere with that color detection. Thus, if something on the road, such as a white arrow, is present, then my road color detection will fail. In terms of software, this could be resolved by looking at a large area of the road, hoping that the average color of the road will dominate over any road markings. Another approach is to implement a road color memory that will average what is presently seen with what the road color has historically been. In terms of hardware, having a camera that automatically responds and adjusts to the light intensity coming in to try and maintain a certain brightness of the image could eliminate some of the need for road color detection in the first place. Another challenge I was faced was the initial flash of the camera as its shutter opened to start the video. In both videos, you'll see that the lane lines are inaccurate for the first second as the camera adjusts. In the second video, when the car changes lanes, there is a brief period where the lane line detections becomes inaccurate. This is a result of the old lane line exiting the frame and a new lane line entering the frame from the other side. Since my algorithm averages the line over time, this sudden jump in position cannot be quickly responded to. I could decrease the memory of my algorithm to allow it to respond faster, but this could compromise its ability to maintain a view of the dashed lane lines. I think a possible solution would be to apply a weighted average to more recent images to allow the algorithm to treat newer images more highly, thereby responding to lane changes faster. It also may be better to not split the algorithm's processing into a left and right half, and instead determine if a line is a left or right line by whether it is in the left or right half of the image. This would ensure that line seamlessly transitions across the image rather than disappear from one half of the frame to the other. In the second video, the algorithm also had trouble with detecting too many white lines at one point. As the car was passing a merge lane, it detected the additional lane lines from the merge lane, causing it to inaccurately determine the orientation of the lane line. To correct this, the program may need to weigh more heavily lines that are detected closer to the center of the image rather than farther out. This would help ensure that the lines being seen are the ones relevant to the car rather than other cars. Lastly, there was a period in the second video where a car on the left casted a shadow which partly obscured the left lane line. To account for this, I may need to observe road color more closely to the lane lines themselves in case they are within a shadow. This has been my ENME435 Assignment 4 project. My name is Aidan Stark, and thank you for watching.